Hello and welcome to WinXAS Tutorials, where eventually I want to talk about analysis of XAS data from time-resolved studies. A lot of the topics and procedures we talked about in previous tutorials will come together here to analyze a series of XAS spectra. As always, the WinXAS software and the XAS data I will be using in the hands-on session can be obtained from the WinXAS website. For clarification, single spectra measured under reaction conditions in situ operando, or however you like to call it, do not require special treatment. All procedures we talked about so far are applicable to both a spectrum measured at room temperature in air or a spectrum measured at 700 Kelvin in hydrogen. Time-resolved experiments, regardless of conditions, yield a series of spectra ranging from a few 10 to several hundreds. While it may be possible to analyze all spectra individually step by step, this would be rather time-consuming and inefficient. Additionally, more often than not, we analyze such series of spectra to reveal characteristic evolutions of parameters with time rather than absolute values. This requires all spectra to be treated exactly the same, which in turn calls for some sort of automated analysis procedure. This procedure should be flexible and permit using any of the previously mentioned data analysis steps. Before we go into details with such a procedure, let's talk about the origin of WinXAS and some core design choices. When I started writing WinXAS for my PhD thesis, we were using energy dispersive or EXAFS for time-resolved experiments. The spectrometer employed a position-sensitive diode array detector with a minimum measuring time in the millisecond range. Back then, computer memory was slow and expensive, so we used binary multi-column files for rapid access and small size. Those files contained 100+ spectra, and we needed some means to quickly read and analyze those spectra in some serial automated manner, preferably using a graphical interface. For this purpose, a number of numerical algorithms and XAS analysis routines were added to the core of reading and calculating EXAS spectra from raw data files. Later, during my postdoc, I did some time-resolved X-ray diffraction, and again we needed certain procedures to analyze series of diffraction patterns, so I added those to WinXAS. I hope this explains some of the features you still find in the software to this date. Analyzing your own data from time-resolved experiments will probably consist of the following steps. First, individual raw data files need to be converted into a single multi-column file. This can be done for any two-column or multi-column ASCII file with or without energy calibration, depending on the format of your raw data files. Here one needs to keep in mind that the resulting multi-column file contains a single energy axis, which normally makes energy calibration of raw spectra mandatory. Second, you write a macro containing the data reduction or analysis steps you want to apply automatically to all spectra in the series. Third, you use this macro for the automated analysis of all spectra in the multi-column file while choosing what kind of output you want to save. Eventually, you may want to display the resulting traces or fitting parameters, for instance, or export the multi-column file to a single or multiple ASCII files for subsequent use outside of WinXAS. Coming next is the hands-on session. Objectives will be performing the before-mentioned 3 steps analysis of a series of XAS spectra from a time-resolved experiment, which are generating a multi-column file, writing various macros for data reduction and analysis, and eventually look and export the resulting curves or fitting parameters. Data reduction and analysis will include normalization, factor analysis, LC, XANES fitting, atomic absorption correction, and XAFS refinement. For details of any of these procedures, please refer to previous tutorials. XAS spectra of samples and references, as well as theoretical phases and amplitudes for XAFS refinement, are included in the tutorials data folder, which can be obtained from the WinXAS website. Let's get started and create a multi-column file. With all things WinXAS, you need to open a data file for this. This should be one of the data files you want to use in the multi-column file. There are two reasons for that. First reason being you need to tell the software what kind of file format you're using in case you want to calculate the spectrum or the reference from a multiple column ASCII file, so a raw data file basically. Second reason is that this is the file you are going to use for the energy calibration if you do want to do an energy calibration when you create the multi-column file. This does not necessarily have to be the first spectrum in the series. It can be the last spectrum or it can be somewhere in the middle. That totally depends on your experimental settings and on the series you are working with. So that being said, this is our data file, and now we can go to time resolved and create a multi-column file. So here now we need to select all the files, all the raw data files we want to include in the multi-column file. All those files are included in the MO3 operando folder in the WinXAS Tutorials data folder. In order to get the order right here, you need to select the files from the last all the way to the first. So when you do it this way, then you get the right order. You see 10, 11, 12. So this is then the right order of the data file. This is not a WinXAS issue. This is a Windows Explorer issue that has been in Windows for ages, and I do not expect that to change anytime soon. So this is the way we have to deal with this. So those are the files that we want to include in the multiple column file that we are about to create. So now we can click on open and we get this box. So we want to calculate the EXAFS spectra from the raw data multiple column file. So this is pre-selected. We do want to do an energy calibration because, as you will see, there is a slight shift in energy. There can be a slight shift in energy from spectrum to spectrum, and you want to account for this slight shift by energy calibration because, as I mentioned previously, the multiple column file only has one energy axis and all the other columns then are the spectra. So we do want to do the reference. We want to have the reference spectrum calculated from the multiple column ASCII raw data file. So now we can click on calibration, and this opens the box, the dialog that you already know for the energy calibration. So the program calculates the metal foil reference spectrum for the currently loaded file. So this is the reference that is in the very first file that we opened. So this is molybdenum metal foil, so we want to use the first inflection point, so the root and the second derivative. We select the range, let's say from here to here, root, second derivative, and OK. So that will set the range, and this range will then later be used to search for the inflection point, so for the root and the second derivative, and it will take this root as the edge position of the molybdenum metal foil. So now we have to set the tabulated value for molybdenum, And this is basically it. So now we can calculate this. This is a file name that is suggested. Here, C for calibrated, you can call it whatever you want. So, okay. So now this is the energy calibration done. You see all the files that are included now in this multiple column file. And you see the energy or the result of the energy calibration. So this is basically the difference to the tabulated molybdenum metal KH position. And you can see there is a slight shift here from spectrum to spectrum in this series. And so all the spectra now have been energy calibrated and saved in this one multiple column file. So now we can open this file, extension DXA, and this is the file that we just generated. Open it. So now this is the first spectrum in the series. There is a number of spectra, as you can see here, all the way to 50 spectra in this series. So to see if that was successful, actually, it's a good idea to just display all those spectra. And so we go time resolved, multiple column plot, and we can just superimpose all the spectra in one plot. And well, that's what we get. And you see there's a typical isospecifical points here. And so this is a series of spectra. Apparently there's some chemical reaction going on there, and we're going to analyze this set of spectra now using the macro capability and the automatic macro analysis feature here. So the next step in EXAFS data reduction now is background correction. Energy calibration is already done when you create the multi-column file. So now we can go straight to background correction. So we want to write a macro now that we can apply to the entire set of spectra and do the background correction. So we go to the macro recorder, call it background save. So the first thing actually you want to do when you create a new multi-column file is to shorten the range a little bit. You can see there are some artifacts here that are actually from the measurement, but there can also be some points off because of the energy calibration. So before you actually continue with any meaningful data reduction step, we just want to shorten the range a little bit. So the very first step in this macro will be just section and cut a few points at the beginning and at the very end. Okay. So now, next step is the background correction. We're going to use the 2 polynomial with 1 and 3 for the post and pre-edge region. So let's start the post edge. Here we want to use the range where we have a mostly linear decrease of absorption with energy. So that would be, let's say, up to here. And we can use this range then for our first order polynomial in the pre-edge region. And in the post-edge, we're just going to use the entire range for the third order polynomial fit. That looks decent. And then we can just click on OK. And we get the background corrected and normalized absorption spectrum. So now we can stop the macro recorder because this is all we wanted to do. So we can stop this, and now we can apply the macro to all the spectrum, all the 50 spectra in the series. So this is time resolved and automatic macro analysis. And basically all you have to do now is select the range, but you want to use it on all the spectra in the series, and we want to save whatever traces we get. So we want to save the background corrected and normalized absorption spectra. And so we can just call that C and then B for the background correction and normalization. So, okay, and now we select the macro that we just created, click on OK, and this is it. So now we have all the spectra in the series, background corrected and normalized and saved in another multi-column file that we're going to open now. Here it is, CB, open it, and so this is what we just created. So now again, we can just display all the spectra in this multi-column file, see if the normalization and background correction went well for all the spectra in the series. So we're just going to superimpose all of them, and again, that looks decent enough. So those are the spectra now that we're going to use for the XANES and the EXAFS analysis. So XANES analysis first, we want to do principal component analysis, we want to do LC XANES fit, and we just want to determine the edge position. So for the XANES analysis, we're going to shorten the range a little bit to the XANES region. So the next macro actually will just be cut XANES. Save, again, section, and then we are going to shorten the range a little bit to the XANES region, something like that. Okay, that's all we wanted to do. So again, we can now apply the macro to the file, call it XANES. Okay, use the macro and create the next multiple column file. So we open the multiple column file that we just created with the XANES data. So now for the principal component analysis and also for the LC XANES fit, we need some references. And we have raw data files for the references, and so now we are going to create the appropriate reference files using basically the same macros that we just used for the data reduction of this set of spectra to this point. So I'm going to open, and now we exceed the number of open windows. So that can happen when you just go from one file to the other. So we are going to close all the files that we do not need anymore and start again. And now start with the references with raw data files again of the references that you can find in this data folder. There's a molybdenum dioxide and a molybdenum trioxide references. Let's start with the molybdenum trioxide measured at reaction temperature. So basically the run that we are working on here was measured at roughly 400 degrees Celsius. And so we have a molybdenum trioxide reference. That the molybdenum dioxide reference we're going to use was measured at slightly higher temperatures, but this should be good enough for the analysis that we are going to do here now for the XANES. So let's start with the molybdenum trioxide. It's the same data file format, so we can just calculate the spectrum. So now here we have to do the energy calibration by hand because we do not have a macro for that. We just use the energy calibration that comes with the creation of the multi-column file. So we go to EXAFS, energy calibration, and we basically do the step again that we just did with the creation of the multi-column file. So second derivative, okay, and it's the molybdenum KH. So now this is energy calibrated, and now we can use the same macros that we used for the analysis of the multi-column file. So this is just one macro or one spectrum now that we want to analyze. So just start the macro, for the background. And then again to just cut the XANES. So now this is our molybdenum trioxide reference now that we're going to use for the principal component analysis and also for the LC XANES fit. So we are going to save this, call it MO XANES. Okay. So that's the molybdenum trioxide reference. We need to do the same now for the molybdenum dioxide. So this is the spectrum, same data file format. We need to do the energy calibration. Same procedure here, molybdenum, and then we can do the background correction, and we can just cut the XANES region. So this is our molybdenum dioxide reference now, and we're also going to save this and this format now as molybdenum dioxide reference. Save. Okay, so now we do have the references that we need. Going to close those windows again and continue with the multiple column files that we created for the XANES analysis. Open this. So first thing we want to do is the principal component analysis. We want to see whether those two references that we have, the two spectra of molybdenum dioxide and molybdenum trioxide, are actually appropriate references to describe the mixture of phases that we have apparently present in this set of spectra. Whether two references, two spectra are actually sufficient to explain or to describe this mixture. So we go to the vector PC analysis. And another advantage of the multi-column file is that you can just directly use those columns for the principal component analysis. So we just click on OK. So now we do actually have a large number of spectra now, apparently. And we can now try to reconstruct. We need at least two spectra, two references, two components to reconstruct the spectra. Click on reconstruct. And we see now, looking at the residuals, so there is still what looks mostly like noise. So probably two spectra, two references are sufficient to explain this series of spectra, to explain those or describe those mixtures. From the indicator here, you can actually see that the minimum in the indicator is on the third component. So there may be a third minority component here that we do not have in our reference database. And so we're not going to include this, not being able to include this, but that's just something to keep in mind. This is not the temperature. So if that was a temperature programmed experiment, then I would suggest this to be the temperature. But this is an isothermal run done at a constant temperature of 400 degrees Celsius. So this third component here, this minority component, cannot be the reaction temperature, change in reaction temperature, but it may actually be a third component. But we're just going to go with the two references that we have available now, for now. So two references, so we're going to do the target transformation and use those references that we just created. Start with molybdenum trioxide. So good match between the reference and the target transformed spectrum. So no surprise there. We start with molybdenum trioxide at this temperature, so that should be a good match, so we can use this. And then the next one is the molybdenum dioxide reference that we just created. And again, we get a decent agreement also with the molybdenum dioxide. So those are most likely the two major phases that we have present in this reaction, in this phase mixture, in this set of EXAFS spectra. So now that we have found the two references that we can use for the quantification, we can have a look at the concentration that the program calculates now from the principal component analysis that we did so far. And so this is the evolution of the phases now. So we start with molybdenum trioxide, we get a reduction basically of molybdenum trioxide and formation of molybdenum dioxide. And you can see this characteristic shape here of those functions that I'm going to talk about a little bit soon when we have the LC-XANES fit performed. So this is the principal component analysis. We have identified the two references that we can use now for the quantification using the linear combination fit. So we can just cancel this here and continue with the linear combination fit. So for the linear combination fit, we just need the next macro that we are actually going to write using the XANES spectrum here of the first spectrum in the series molybdenum trioxide. So record a new macro that we're going to call LC-XANES. Save. And then we go to the linear combination XANES fit, and we are going to use the two references that we just identified by the principal component analysis to sufficiently well describe all the spectra in the series. So those are the two references that we are going to use in the range. Okay. So now at this point, you actually want to use constraints of the parameters, because in this analysis, we may actually be going from 0% molybdenum dioxide and 100% molybdenum trioxide to 100% molybdenum dioxide. And in order for those refinements not to, for instance, result in negative partial concentration or way too large E0 shift, we're going to constrain those parameters. So for the concentration, we are going to constrain it from 0 to 1 for the concentration, and the E0 shift we are going to constrain from, so we are in KeV, so that's basically from -3 to 3 EV. That should be absolutely sufficient range for the slight adjustment of the absorption edge. Okay, so concentration again from 0 to 1, and the edge shift from minus to plus 0.003. So that's fine, that's the starting parameters, and now we can just click on OK, and this is going to perform the refinement. And as expected, because this is the first spectrum, we get roughly 100% molybdenum trioxide and no molybdenum dioxide. Okay, and now the program wants to calculate confidence limits and the f-test. At this point, you do want to cancel this, because otherwise the program is going to ask with every single refinement in the automated macro analysis if you want to do this. So no, we do not. And so we actually just cancel it, and now we can stop the macro recorder, and we have our macro for the automated analysis now of this series. So we can go back to automatic macro analysis, and at this point now, we do want to save the fit parameters. We do not want to save the traces, because the traces, if you save the traces here, you would just get the same file again, because the program just then saves the XANES files. But those we already have. What we do want to save are the fitting parameters from the linear combination fit. and those will be saved with the extension PAR. So XANES, and this is the linear combination. So we can just click on OK, select the macro, open it, and this is going to perform the refinement, and done. Fine. So now we can open the file that was just created, apparently extension parameter. Click on OK, and those are now the concentrations of the references in this series of spectra. The x-axis always is the number of the column, basically. So if that was time, or if you wanted to transform it into time or temperature or whatever the parameter is on the x-axis, then you could of course do this, but the program basically now only displays the column number. There's no further information available there. So this is the first column. The next column now would be the energy shift, and then this is the concentration of the trioxide, basically. This is the order we had this, so this is what we get. So again, blue trace now is the concentration of the molybdenum trioxide. We start with molybdenum trioxide. We observe the reduction of molybdenum trioxide to the dioxide and the formation of molybdenum dioxide. And apparently this does not go to 100%. So at the end of this run, we do not see complete reduction here. There is the rate slows down. It starts fast, but then apparently there's a change in the rate limiting step here. And this, of course, can also be analyzed now. Since we do have a time-resolved experiment, we have some time axis here, basically. So this is an isothermal run, so we could easily convert the x-axis into reaction time. And so since we have a time axis, we can actually do some kinetic analysis if we wanted to. Since we do have those traces, might as well use them and do some kinetic analysis. And there are some ways to do this implemented in the software. I'm very briefly just going to introduce them. For this brief excursion to solid-state kinetics, let's cut the induction period from this trace, and in XRD we're going to use the kinetic calculator. So since this is an isothermal experiment, we can roughly interpret the shape of the traces in terms of suitable models for the rate determining step in those ranges. And for this, you see here, there's a number of models available for the rate determining step. And basically they are divided into two groups, an acceleratory and a deceleratory group. So the idea here is those are the so-called integrated models, and what we're looking for is a way to linearize the traces that we see here. So if we start with the first region here, we have a increase in reaction rate, so we need to use acceleratory models. And as you see, when we start with the power laws, or we go to some nucleation growth kinetics, we get a reasonable linearization in this range here up to 20, I would say. So in this region, we can describe the rate determining step as being limited by nucleation and growth. At about 20, there seems to be a change in the rate limiting step. So if we go back, we have an acceleratory, and then we're seeing a transition into a deceleratory range here. So to describe this range of the trace, we need to use this deceleratory model. So if we go to one-dimensional, two-dimensional, or three-dimensional diffusion, you can see there is for three-dimensional diffusion, there is a reasonable linearization here in this range from 20 all the way to the end. So basically what we are seeing is, and this is just schematically depicted here, what we are seeing when we start the reduction of molybdenum trioxide, we have a nucleation and growth kinetics, so formation of nuclei. There's an increase in the interface between molybdenum trioxide and dioxide, and the larger the interface, basically, the larger the reaction rate, up to a point where those nuclei overlap, and we see a decrease in reaction rate. This is the regular nucleation and growth kinetics. As an alternative, in this range, we can observe, or we may observe, the formation of a product layer on our particle, and then diffusion through this product layer may become rate determining. And this is actually what we see here in the experimental data. We have a transition to a three-dimensional diffusion as a rate limiting step. So we start with nucleation growth, and then we get diffusion controlled with the ongoing extent of reaction. So this is basically a model approach. So we are using models for the rate determining step. And from those linearized regions now, here we can do linear regression and we get the slope, and the slope basically is the rate constant. And so if we measure different reaction temperatures, we can determine the rate constant at the different temperatures and then assemble an Arrhenius plot and determine the activation energy. However, this is a model approach, and you see there is some ambiguity in determining suitable models for the linearization. So it would actually be nice to have another approach that is model independent and that allows us to determine the activation energy without any assumption of suitable models for the rate determining step. And this basically can be done with the isoconversional analysis. And this is shown here. For different traces measured at different temperatures, you can basically determine the activation energy as a function of the extent of reaction, and then use this activation energy as a guideline to distinguish suitable models for the rate determining step. However, this is well beyond the scope of this tutorial, and I assume you are here for the EXAFS data analysis, so let's continue with that. The last step in the XANES analysis will be determining the edge position as a function of time in this case, and convert the edge position into average valence. For this, we go back to the series of XANES spectra that we created previously, and so now we are going to look for a feature that shows a rather large dependence on the reaction time and use this feature to determine the edge position. For that, it's a good idea to just superimpose all the spectra and look at the spectra, look at this trace, and search for suitable features. So obviously this can be the edge position. So we see the typical change from molybdenum trioxide to molybdenum dioxide, shifting the edge position to lower temperatures. But we also see there are other features in the XANES, in particular this maximum here, that shows an even larger shift as a function of reaction time, in this case, as compared to the edge position. So this is actually what we're going to use. We're going to use this maximum. We determine this maximum automatically in this series of spectra, and from this maximum then determine the edge position as a function of time. So now we want to make sure that we select a range that includes the maximum in the first and in the last spectrum, of course. So we just go all the way to the last spectrum, and then we can just superimpose the two, so we have molybdenum trioxide and basically what is mostly molybdenum dioxide, and those are the two features now. Those are the maxima that we want to determine in molybdenum trioxide and molybdenum dioxide spectra. So the range that we are going to use should start somewhere here, and then we can just go from here to here. So this should be the range in which we want to use or want to search for the maximum in the XANES spectra. So that of course means we need to write another macro for this search that we're just going to call max. And first step here is to select the range that we want to use. So let's put that from here to roughly here. Okay, and then in this range we are going to search for the maximum. And we only want to save the highest value. We want to save the maxima only, and we do not need any further smoothing. So, okay, that will search for the maximum, the x position of the maximum. It also save the height, which we're not going to use, but it saves the position. So, stop the macro recorder, and then we can go to automatic macro analysis. Again, we want to save the parameters. We want to save this position. We do not want to save the region that we cut from the XANES, but we do want to save the edge position, and we are going to call this max. Okay, we select the macro, and that's it. And now we can go and open the parameter file max, and this is what we get. So this is now the evolution of the edge position, of the position of this maximum as a function of spectrum number, basically, which is a function of time in this isothermal experiment. So now we have the edge position as a function of time, and now we of course would like to convert the edge position into average valence. And we can do this from the references that we have. We have a molybdenum dioxide and a molybdenum trioxide reference, and so we can basically from those 2 points construct a calibration curve that we can use to convert edge position into average valence. And I prepared this. So what I did is I basically used the macro for the analysis of the molybdenum dioxide and molybdenum trioxide spectra, and then put this into just a text file, basically valence text. So we can just open it, go to file information, and so this file basically is only 2 data points. It's the edge position here on the x-axis and the average valence on the y-axis. So this is molybdenum dioxide and this is the molybdenum trioxide. So this is just those 2 data points. So what we want to do now is we're going to close this again, because what we want to do is we actually want to not open but load this calibration trace into the same window as we have open here with the evolution of the edge position. So we just go to load and we load this into this window. So now we have both of them, our calibration and the evolution of edge position. So what we can do now is we can use a linear regression here and just determine a linear function, and then we can go back to this trace here, and now we can actually apply the linear function that we just generated to the y-axis. So this is in edit, modify ordinate, and we just go to external function. External function in this case refers to the the WinXAS function to the linear function that we just generated from the linear regression. So we can just use this, apply this function to the ordinate, to the y-axis. You can just click on apply, and you see this converts the edge position into average valence. And so now we have the average valence as a function of spectrum number or as a function of time for this isothermal experiment. And we get a similar shape, of course, compared to the LC XANES fit. And we can also see we do not get a complete reduction to molybdenum dioxide as expected. We are here at about 4.2. So we have an average valence at the end of about 4.2. So if you compare this to the linear combination fit, where we get an amount of molybdenum trioxide at the end of about roughly 8 or 7%, and we convert those 8 or 7% molybdenum trioxide into an average valence, we end up at about 4.15. You can, of course, calculate this for yourself. And so from the linear combination fit, we get an average valence at the end of this run of about 4.15, and here we end up at about 4.2. So that's a good agreement and confirmation between the average valence calculated from the edge position and the linear combination fit, the phase analysis based on the reference spectra, based on the XANES, and convert this into average valence. So those two agree quite well. So this ends the XANES analysis. So next now is the EXAFS analysis. Let's start the EXAFS analysis with some general remarks. When analyzing a series of spectra, you need to find a procedure that you can apply to all the spectra in the series. In most cases, this will be more time-consuming and more difficult than just a single spectrum analysis, and it will quite often involve some back and forth and trying different ranges, trying different approaches, in particular to the atomic absorption refinement, until eventually you arrive at a procedure that you feel comfortable with using for the entire series. For the sake of brevity in this tutorial, I will just show you the procedure that I came up with for analyzing the series, but of course, please feel free to experiment and to try your own procedure, try to come up with different solutions to this problem of analyzing all the spectra in the series. So what we want to do is now to extract the chi of k, so calculate the XAFS function and then use this XAFS function for simulation and XAFS analysis. So we already have the multi-column file that contains the background corrected and normalized absorption spectra. So we can basically proceed now with E0, so the energy threshold for the spectrum, and convert the spectrum into K-space and perform the atomic absorption refinement. So we are going to write the next macro to convert the spectrum from the energy space into the K-space. This is all we want to do in the first step. And in general, I would recommend to break down the analysis into as many individual steps as possible and always verify the intermediate results, verify the spectra that you calculate in order to make sure that the procedure that you applied actually resulted in whatever you were expecting, and that there are no glitches or whatever in your data. So conversion, we use the E0 first and second derivative, and it's basically very similar to what we already did in the previous tutorial when we analyzed the molybdenum trioxide, molybdenum dioxide mixture. We are going to use this feature here, the basically second inflection point, the maximum in the first derivative here, which corresponds to this root in the second derivative, and we select the range that includes this root in the second derivative. And of course, in principle, you need to make sure that this range now includes this root for the entire series, for the entire set of spectra that you're going to analyze. So not only the first one, of course, but this has to be also applicable to the last spectrum in the series. So we use this, we search for the root in the second derivative, and okay. And the next step then is conversion. Use this energy threshold to convert from the energy space into the K space. So this is all we want to do in this macro. And so now we can apply this macro to this file, call it conf, okay, and then we just use the macro that we just created. And already done. So now we can open this file and just verify that all the spectra that we calculated actually are no glitches, no outliers, that everything looks reasonable, and that we can continue using those spectra now with the atomic absorption refinement. So the next step is atomic absorption. The next macro, we're going to call this mu, save, and then next step is the mu0 fit, the atomic absorption fit. We're going to use the cubic spline fit. And we are going to perform this refinement in the range from 3 to 14 using 8 spline knots. And this is the procedure that I mentioned earlier. This is the procedure that I found suitable for analyzing the entire set of spectra. So fit that results in the atomic absorption, corrected EXAFS function, and okay. So this is still K cube weighted. We want to remove this weighting before we save the resulting EXAFS function. So we go to K weighting 0, and then this is the XAFS function, just the chi of k now, that we want to extract from all the spectra in the series. So we can stop the recorder and again apply this macro to this data file, call it mu, and just perform the atomic absorption with this procedure for all the spectra in the series. So again, we open the file that we just generated, and we can confirm that all the spectra are looking okay, that we get a nice transition from the chi of k of molybdenum trioxide to the chi of k of molybdenum dioxide, or mostly molybdenum dioxide, as we know from the XANES analysis. So now we have our XAFS chi of k, and we can use this now to calculate the radial distribution function, so for the Fourier transform, and we can use it for XAFS simulation and refinement. So before we do the XAFS simulation and refinement, let's calculate the pseudo-radial distribution function with a new macro calling this FFT, and calculate the Fourier transform using the settings that we used all the time now. Okay, and that will calculate the pseudo-radial distribution function. And this is all that we want to do in this macro. And again, we can apply this macro to all the spectra in the series. Just call it a T and use this macro. So now again, we can open this new file ft, and we can now display the pseudo-radial distribution function again and see the transition from molybdenum trioxide to molybdenum dioxide. Maybe just briefly, we can also, of course, look at some 3D plot here, and what we see is we start with molybdenum trioxide and we reduce molybdenum trioxide to molybdenum dioxide. So at the end we have the characteristic pseudo-radial distribution function of molybdenum trioxide. We can rotate this, so molybdenum trioxide here and molybdenum dioxide over here, and this looks all very nice and reasonable. And so now next step, last step that we want to do actually is analyze the EXAFS, do some EXAFS refinement actually, and try to extract some parameters, some structural parameters that we then can display as a function of time. In this case, since, as I mentioned before, this is an isothermal reduction experiment, so we can extract structural parameter as a function of time when we analyze those XAFS spectra, and this is what we want to do in the next step. For the XAFS refinement, we always need to start with a chi of k. We cannot start with the radial distribution function because for the XAFS refinement we need the magnitude and the imaginary part, and here we only have the magnitude. So this is also a reason why you always want to save the chi of k for display and also for the XAFS simulation and refinement. So we go back to the chi of k and start with the first spectrum, which basically corresponds to molybdenum trioxide at about 400 degrees C. So we do the Fourier transform and we do the XAFS simulation using the molybdenum trioxide theoretically calculated phases and amplitudes that we already used in a previous tutorial. So with a weight of 10, going to use all those scattering paths for molybdenum oxygen, molybdenum, and those multiple scattering paths that we need for reasons that we also discussed previously. Transfer and OK. So for the simulation, we're going to use the correlated Debye model to estimate Debye temperatures with a much higher Debye temperature here for the oxygen sublattice compared to the molybdenum sublattice. And we're going to use the reduced amplitude for the multiple scattering path in the calculation of their Debye-Waller factors. So, okay. And so now we are getting experiment and theory, and we already can see we get a reasonable agreement between the experimental and the calculated chi or Fourier transform in the molybdenum shell. Not so much maybe in the molybdenum oxygen shell. Here we see some deviation and some discrepancy in the amplitude. So if we now look at the individual scattering shells that actually contribute to this discrepancy here in the amplitude, we can basically identify this shell here, this distance at 2.25 angstrom. And if we reduce this distance a little bit, we can basically obtain a much better agreement between experiment and theory. So apparently molybdenum trioxide at 400 degrees C, or at least this what was used here as a starting material, we need to change those starting parameters a little bit to account for the difference in the amplitude. So okay, we can use this now to do the XAFS refinement. Going to use all those shells or paths, and we're basically going to repeat what we already did in the previous tutorial with respect to refining the mixture. So we have a single E0 shift. The Barwola factors, we're going to refine them all the same for molybdenum oxygen path and for the molybdenum path together with a multiple scattering path. Similar to that, the distances, the molybdenum distances and the multiple scattering path distances will all be refined with the same delta R with respect to the theoretical values. Same for molybdenum oxygen, except for this one that we were just looking at, that we are going to leave free in the refinement. So we're going to switch over to delta R, constrain those parameters, and now we have 6 free running parameters here in this refinement for the molybdenum trioxide structure. I'm going to start the refinement, okay, and we are getting a reasonably good agreement between experiment and theory, reasonably good in particular, because we have a very reduced number of free running parameters that we want to have for a stable refinement that we can then use later for the analysis of the entire series of XAFS spectra that is the subject of this tutorial. So this is the first spectrum in the series. This is molybdenum trioxide at 400 degrees C. Now we can go to the last spectrum, which will be mostly molybdenum dioxide at 400 degrees C, and see what kind of refinement we can obtain there. So let's switch off the display of the imaginary part and the display of the function, and then we can go all the way to the last spectrum in this series, so the molybdenum dioxide, and again calculate the Fourier transformation and do the EXAFS simulation. Now using the theoretical phases and amplitudes for molybdenum dioxide in this monoclinic modification that we used already before. So going to decrease the weight a little bit, same as we did before, and so those are the scattering shells that we're going to include now, single and multiple scattering shells that are necessary to describe the radial distribution function in this range. Transfer, okay, and going to do the same here, so calculate the Barwola factors from the correlated Debye model and just have a look at the simulation. Again, we can change the parameters here. Now we only need to reduce the Debye temperature a little bit, and we already get a quite decent agreement between experiment and theory in this case for the molybdenum dioxide, or mostly molybdenum dioxide at 400 degrees C. This corresponds to the last spectrum in this series. So again, we can do the XAFS refinement using those scattering paths, and basically the same approach. We're going to fix all the coordination number, use 1 E0, and here we are also going to correlate the Barwola factors for the molybdenum oxygen shells to be the same, and the one for molybdenum and the multiple scattering path to be all the same in the refinement, and the same with the distances. So the molybdenum oxygen distances, or the delta R for those distances, and also for the molybdenum will all be the same, and we switch to the delta R. So here we have one less parameter free running parameters, so 5 compared to the 6 that we had for the refinement of the molybdenum trioxide spectrum. So now we can start the refinement, and also here in this case we're getting a reasonable good agreement for this reduced number of free running parameters between experiment and theory. So good description of the molybdenum dioxide structure that is present at 400 degrees C at the end of this experiment. So now we have the first and the last spectrum analyzed, and we have established procedures for describing the molybdenum trioxide structure at 400 degrees C and the molybdenum dioxide structure at 400 degrees C. So now raises the question, what's with the spectra in between? As you may already have guessed, those of course correspond to mixtures. Yeah, we know from the analysis of the XANES, from the LC XANES fit, that we have mixtures of mostly molybdenum trioxide and molybdenum dioxide. And from the LC XANES refinement, we know the ratio of those mixtures in the individual spectra. And we can use those ratio, similar to what we did in the previous tutorial, to refine a mixture or a combination of the two theoretical structures for molybdenum dioxide and molybdenum trioxide to those spectra of the series. And this is what we are going to do for one spectrum now, and then we are going to try to apply this in an automated analysis. For a spectrum that corresponds to a mixture, let's pick column number 20. So we can do Fourier transformation, and now we know this corresponds to a mixture of the two oxides, and the concentration we can actually obtain from the LC XANES fit results. So we can go back to this parameter file, open it, and we get the phase evolution for the first phase. So this starts at 0. So this corresponds to molybdenum dioxide. At column 20, we are at roughly about 55% molybdenum dioxide and 45% molybdenum trioxide. So that ratio of the two phases we can now use in the simulation and the refinement of the EXAFS spectrum in column number 20. So let's start with the EXAFS simulation. We're going to use separate files now for the molybdenum dioxide and molybdenum trioxide phase. You always have to select this first, and then we select the molybdenum dioxide first. So basically do the same that we just did for the analysis of the last spectrum. So that's molybdenum dioxide, and then we do the same for the molybdenum trioxide. Here also add those scattering path to the simulation. And okay, for the concentration, we're going to select what we just determined from the LC XANES fit results, 55% of the first phase, which is molybdenum dioxide, and 45% for the trioxide. And since we know this number from the XANES analysis, we're going to keep those concentrations invariant in the refinement. So, okay, and just for the simulation, just going to copy and exit, and so this is a reasonably good agreement for starting parameters for the refinement. So we can jump right at the refinement and basically just select the range, keep all the phases and the concentrations that we have selected, click on OK. So now we have to significantly reduce the number of free running parameters, basically use the same correlation and constraints that we established for the single phases. So we're going to fix the amplitude reduction factor, fix the coordination numbers. For the Debye-Waller factors, we are going to correlate the molybdenum oxygen and the molybdenum for the molybdenum dioxide. Here you see this number changes from 51 to 1. So this is all molybdenum dioxide, and here basically start the molybdenum trioxide. So those are all to be refined the same for the molybdenum dioxide. Similar distances. The delta R is going to be the same for the molybdenum oxygen and for the molybdenum distances. So this is all for the molybdenum dioxide, and so here we have the molybdenum trioxide now. The Debye-Waller factors going to do the same here for molybdenum oxygen path and for the molybdenum path and the multiple scattering path. Here the distances for molybdenum and the multiple scattering path are to be refined the same, and the distances for molybdenum oxygen we're also going to be to keep them the same, except for this one where we saw that we need to have this free in the refinement to get a good agreement. So that's it. And so now we are at 10 free running parameters, so one less than the sum of the two individual phases, because we're only using one E0 shift now. We're going to set some constraints here for the Debye-Waller factors and also for the distances. Keep those flexible, and then we can start the refinement. So, and that's done. And so this is the kind of agreement we get now. We can look at the fit results for the single scattering path, and here we have our concentrations of molybdenum dioxide and molybdenum trioxide, and this sort of agreement here for experiment and theory for this mixture of almost 50-50 dioxide and trioxide. The agreement here seems to be better than what we achieved for the individual phases, but we have to keep in mind that we are refining two phases here now, so we have a larger number of free running parameters, a higher degree of freedom in the refinement. So we would expect a better agreement between experiment and theory for this refinement. So now we have our fit established, and next step is now that we can write this into a macro that we can then apply to the analysis of the entire series. For writing a macro for EXAFS analysis, we need to go back to the chi of k. EXAFS analysis and also writing a macro for EXAFS analysis always starts with the chi of k. No matter if you want to do your XAFS refinement in the K space or in the R space, we always need to start with the chi of k. So we have our macro, let's call it XAS. And the first step always in the macro then, since we do want to refine in the R space, is the Fourier transformation, followed then by the XAFS refinement. So here we actually just want to repeat the previous refinement. We do not need to input all those flags and constraints again. We just keep all flags from the previous refinement. We keep the border and all the concentrations, and so we basically just repeat the previous refinement, click on exit, and just redo it, and okay. And we can stop the macro recorder, and this will then have recorded our macro for the XAFS analysis of a mixture, including those two phases, molybdenum dioxide and the molybdenum trioxide. So before we actually do the analysis of the entire series, let's test our macro with another column, let's say column 25, and we're going to just run the macro, the XAFS fit macro that we just created, and get this result. So now if we look at the fit parameters, actually, we see that the concentration of the two phases has changed. So although those were kept invariant in the macro set to 55 and 45, apparently here now they have changed. So reason for that is that the program actually searches for the results of the XANES fit. And what that is the program searches for this file in particular, the multiple FEF coefficient.par. This file is always generated with the same name when you do the XANES fit in a macro. So this file, when we open it, this file contains only the concentrations of the phases that were used in the XANES fit. So this is the molybdenum dioxide, and the next trace then is the molybdenum trioxide. So now if we go to column 25, which is about here, we see we are at roughly 70 plus for the molybdenum dioxide, and so about 30 for the molybdenum trioxide. So those concentrations basically at those data points, which corresponds to the columns here, will be used in the macro. The most important requirement for this to work is that you use the same order in the XANES fit and the EXAFS fit. So here we start with molybdenum dioxide and molybdenum trioxide, so dioxide, trioxide, and the same order you need to keep when you do the multiple phases EXAFS analysis. So this is why we also here start with the dioxide and then the trioxide. If you do not want to use this file here, this parameter file, for the refinement for whatever reason, then you need to either delete it or rename it. If it's there, the program is going to use it. So, okay, so this is column 25. We can do the same, test the same now, let's say for column 16. Let's load column 16 and apply the macro. And so this is the refinement, and those are the results. And here we are at about 42% molybdenum dioxide and 58% molybdenum trioxide, according to the XANES fit results. So again, those are the concentrations taken from the XANES fit results. So this is how this multiple phases EXAFS procedure works when you combine the XANES analysis with the EXAFS analysis, when you combine the XANES fit to obtain those concentrations, those phase concentrations, with the XAFS refinement, where you use those phases then to refine a sum of those two to the experimental spectrum. So now we have the macro, we have tested the macro, and it seems to be working okay, and now we can apply this macro to the entire series of spectra. However, before that, we need to talk about some limitations of this approach, refining multiple phases to an experimental XAFS spectrum. Apparently, in general, it's not a good idea to start a refinement with free running parameters that do not influence the amplitude of the theoretical function. Unfortunately here, this would be the case if any of those concentrations had a value of 0. So if we do not have molybdenum dioxide, for instance, which applies to the first spectrum in the series, we start with molybdenum trioxide only, we do not have molybdenum dioxide, so the concentration of molybdenum dioxide is 0, and the free running parameters that we have for the molybdenum dioxide phase would not at all influence or affect the amplitude of the XAFS function, and this would not result in any meaningful result of the refinement. To avoid this, the program actually fixes for those cases the parameters of those phases and removes them from the refinement. This threshold is set to 5%. So any phase with a concentration of less than 5% will actually be will not be considered in the refinement and will not have free running parameters in the refinement. So here, for what we want to show actually is we're going to select or reduce the range a little bit of the automated analysis and start at concentrations of, let's say, more than 10%. So we here at 10, column 10, we are at about 10% molybdenum dioxide, and then let's here say at 40, about 40, we are at 90%. So we're going to do the automatic analysis in the range from 10 to 40, where we have at least 10% molybdenum dioxide or 10% molybdenum trioxide. So now we can start the automatic macro analysis, as I said, in the range from 10 to 40. And we want to save the fit parameters, and I'm going to call it XAS. So I'm going to select the macro. The refinement will take a little while, and I will stop the video here and return once the refinement is completed for all the spectra in the series. So the refinement is done, and we are looking at the result of the last column, column number 40, in these automated analysis. On a side note, if the program appears to freeze during those automatic analysis steps, this is most likely because of Windows actually preventing the screen refresh. So just give it some time and be patient, and in most cases the program will return once the calculation has been finished. So here now we can look at the results. So you find two new parameter files. One contains all the parameters from the XAFS refinement. So all the distances, the Barbour factors, coordination numbers, and everything in the XAFS refinement. Also those shells that were actually kept invariant, and so they are all listed here. In addition to that, the program generates a second file that only contains the free running parameters. So we are going to look at those. And yeah, this is what we get now. So those are the distances. We start with the distance. First phase molybdenum dioxide. So this is the evolution of the molybdenum oxygen distance in molybdenum dioxide with progressing reduction of molybdenum trioxide to molybdenum dioxide. So here we have very little concentration of molybdenum dioxide, and then with increasing concentration of molybdenum dioxide, we see this shift in distance. This is the Barbour factor. We have the fit residual here, so it gets better with the increasing concentration of molybdenum dioxide during the refinement. And then we have the molybdenum distance of molybdenum dioxide, the Barbour factor. And here now we are at the molybdenum trioxide phase. So this is the first molybdenum oxygen distance, this very short molybdenum oxygen distance in molybdenum trioxide. You see there's very little change here, and at the end, with the decreasing concentration of molybdenum trioxide, you get larger scattering here, but little change overall in this distance. Well, anyway, as I mentioned before, this is a tutorial about XAFS data analysis and not so much data interpretation, so we will stop this here and basically come to the last step that I want to talk about in this tutorial. The last step, of course, is data export. So let's say you extracted your XAFS function, or you calculated the radial distribution function, and you have those 40, 50 columns now in a binary multi-column file, and you want to export them to be used in another software. Then there are basically two ways you can do that. There is the save multi-column file to ASCII. That will save the multi-column, the binary multi-column file, to an ASCII multi-column file. So just call that test, save, and then we can open this test file, and you see we get this box now that we always get when we open a multi-column ASCII file, and now you have all your columns here that correspond to the columns, the radial distribution function here from your experimental data in an ASCII format that you then can open in any other software, basically. So the alternative is, let's just close this. The alternative is to extract multi-column file to ASCII. That will create single ASCII files. So basically here for the 50 columns, you will get 50 individual ASCII files, 2-column ASCII files that can just create ASCII output. And then when we go to open and those files have the extension XY, then you see, get a list of all those 50 files now, ASCII files with just 2 columns, basically here for the, in this case, radial distribution function. So those are the two ways to extract your multi-column files, your binary data, basically from WinXAS to be used in any other software. Okay, so this was the last major topic I wanted to talk about, and it concludes this series of tutorials on XAS data analysis using the WinXAS software. If you're still here, thanks for watching, and I hope you found some educational values in those videos. I wish you all the best for performing your own XAS experiments and analyzing your own data. Take care.